I'm very pleased to present to you on Effigy, which is our fire and gas mapping tool. And I'll talk specifically about the way in which um, fire and gas mapping has um, has uh, advanced and in many ways revolutionized how we look at process safety, um, and specifically around a number of different process areas in the oil and gas industry. In the agenda for today, I'll talk specifically about some barriers of adoption on fire and gas mapping software. This is important for us to keep in mind because it will drive the context of the rest of the presentation. I'll talk also about what is particular about Effigy that makes it well suited for fire and gas mapping and for addressing those very challenges that I mentioned in the previous section. I will have a case study of an onshore manifold that will speak on how Effigy can work and how it can make a certain difference vis-a-vis other fire and gas mapping tools. And then I'll have some concluding remarks. So to begin with, there has definitely been a step change in addressing detection coverage when we use computer models. Before computer models, we were relying on heuristics, best practices, certainly some rules of thumb that had some basis on science. For example, the molecular density of a gas, some calculations on radiant heat output for fire, the size of the fire, for example. But there are so many different variables to consider that no one heuristic method can fully address those complexities in a chemical process environment, most of which happens to be outdoors. So when computers began to become more available for these particular types of applications, certainly something great happened, and that is the development of full scenario calculations that allowed us to understand precisely the effect that having detectors at a particular place would have in the reduction of overall risk. Understanding also and I would say manipulating the information in a way that could not have been done before, whether it was through such techniques as volumetric monitoring, point source monitoring, or even path of travel and target receptor monitoring. All of these are very useful heuristics, but they do not hold a candle to computer models. The other thing that computer models have done is not only that they account for physical features of the environment and are able to calculate scenario and detection coverage, but they are actually quite flexible. You can have changes occurring in the environment and you are able to adjust your risk profile and also your detector layout based on them. That's something that is quite difficult to do for the previous methods. And lastly, I think that something that is very difficult to do on heuristics is to do evaluation of what-if scenarios. If you have a particular change that is coming, if you are creating, for example, a new process facility that is adjacent to the one you have, and you want to calculate, okay, what effect that will have. If you're writing, for example, a new piece of equipment, how will that change the obstruction of the space? All of that is much easier to do when you have a 3D model and you are able to calculate scenarios and detection coverages based on that. Now, the other thing that we are, I would say, grateful as a process safety profession is on the advancement of standards related to fire and gas mapping. And really, the first one that comes to the fore is a technical report, which is ISA TR 84.07, and that's the guidance on the evaluation of fire, combustible gas, toxic gas system effectiveness. This one is modeled after ISA 615, IEC 65111, excuse me, or ISA TR 84, and it uses the assessment of risk and risk reduction almost as a basis. So if you are familiar with IEC 61511, there are certainly some similarities between the technical report and the standard. Another standard, I would say, or norm that has advanced our state of the art is Annex B of an FPA 72. The National Fire Protection Association has had the National Fire Signaling Code for many years. And it is one of those prescriptive standards by design. But over the years, it has added, Annex B, and it just has developed it further and further. And if you look at Annex B, it really has become its own performance-based approach. And it in itself is based on a handbook by the Society of Fire Protection Engineers. So it's very good that we're seeing the advent of these performance-based norms. And I would also have to give credit to some early pioneers in the business, like Shell and BP, who have developed their own performance-based codes within their corporate codes of practice, and those are listed here as well. So I would say we cannot look at computational models in isolation. They are in fact driven by the way in which people must behave and the documents that they must produce as a result of a particular type of action. And those are really codified in these standards. However, despite the the advent of computing and the advent of very good standards, there are a number of challenges for the implementation of fire and gas mapping tools. You would think that, especially now, there would be widespread adoption of these type of digital tools. That is not the case. And there are certainly some barriers that we must address. One of them is, at least in my view, is the perception of requirement for specialized technical expertise. Certainly, computer models cannot be done or managed by people who have no particular education. It does take some amount of training. And I would say that has led some lay people in the industry to think of this as being a niche field. Also, there is the the notion that there's a high cost for implementation of these fire and gas mapping tools. I hear this quite a bit. I go into the field and someone is asking, well, I believe that we need to map this particular space. I don't feel confident here. However, I am just going to use what I know, which is my rules of thumb. The other one has to do with the risk of inaccuracy of modeling assumptions. They say, well, these modeling assumptions are based on data, and data itself can be flawed. I don't have good drawings. I do not have a very specific or up-to-date piping and instrumentation diagram. So I will not trust the output from these fire and gas mapping models. And I would say the last two are very, very common as well, and that's difficulty visualizing and interpreting complex outputs, and limited understanding of fire and gas system fundamentals. Those two go hand in hand because they do not only rely on the education of the person performing the modeling, but also of the person who is actually receiving the results of the model. You have to have a certain understanding. And so there is that fear or risk, is that uh, the group that is performing some project on fire and gas mapping, upon turning that project over, may find that the people who are receiving it, their clients, they themselves will not know what to do with that. And I'm also been at the front of such situation where you have a client, it receives a report, and nothing happens afterwards. They continue to do things the way they always have. So there's something to be said about these challenges. And I think that the unfortunate part about this, and it's quite common, is that fire and gas mapping is used in spurts. It's not used consistently. Certainly, it's not used with the type of regularity that allows people to develop some proficiency with it. And in my view, that is quite unfortunate. Uh, so what can be done about it? Well, um, at at Kenexis, we have taken an approach that I think is quite suitable to address these challenges, and our software tool does that particular job of addressing these challenges. And let me refer to them one by one. The first is that it integrates the workflow of ISATR 84.07. And that's important because having that structure allows the user to see that fire and gas mapping is not about fire and gas mapping only. There is a process. In fact, the modeling is just one step out of several that need to be done for a fire and gas hazard assessment. And I think this is important because you cannot take 3D models and computation in isolation. And if you use the norms as a guide, that will help drive that context. So as pointed out here on the workflow, one must identify areas of concern, must identify the risk. One of the important parts is to assess and mitigate hazards or risks. So you have to know what is your hazard and what are the consequences of those hazards before applying your safeguards, in this case, your field devices, your array of field devices, and placing them in such a fashion that they're going to help reduce a certain risk. And then you need to calculate what is going to be your fire and gas system effectiveness after you have established those detectors in that place. So that's the fire and gas system effectiveness with mitigation. Going through those steps is certainly going to keep you uh, from misusing software. And I think that overall, having a software tool that follows the framework of the technical report is going to keep the user in the right path. Lastly, what I would say also about TR 8407 is that it is a technical report that relies on several disciplines coming together to create uh, a final product. And I think that this on itself is going to ensure that you have technical rigor, is going to help uh, reduce the likelihood of error. It certainly is going to improve the quality of your output. Any questions? All right. Moving on. So a second way in which the tool addresses the challenges is that it is fairly accurate because it relies on physical properties of the gas and the fire in order to model their particular risks. This is extremely important, and I'll need to explain. In the specific case of Effigy, it uses radiant heat emitting bodies, or I would say the energetics of fire as an input for fire and gas mapping. And this is important because a majority of the fire and gas mapping models, certainly those that are available commercially, use what is called a ray casting method, meaning that it relies on consideration of obstructions and space. If a detector is obstructed in its field of view by an opaque object, then the understanding, or at least in the model, is that there is going to be no coverage or no detection behind that object. This makes perfect sense in a variety of different cases. This is why a number of tools use it. But certainly, it can be flawed when you're looking for long, thin objects, because a fire can be quite radiant. It can emit energy that is going to move well across that particular model or that particular object. And this could actually be seen very well in this screen. And if I may, I'm just going to put my, oh, where is my pointer? Oh, here we go. This is the conventional approach right here. And this is a detection coverage map. Red represents that there is no detector that is detecting a particular area. The yellow represents that one detector is detecting. Green is two detectors that are detecting. As you can see that there's different types of grades associated with the same color scheme. But what you will notice is that when something like ray casting is used and you have several long, thin structures in the space, that you have quite a few lines where no detection is available. And you can see that by the prevalence of red within the space. Whereas when you're using the energy of the fire itself as your physical principle, rather than obstruction only, the area of coverage that one can see is far greater. So uh, uh, it is, I think, clear that this area is represented by much more green that you can see in the conventional approach that is seen above. So these are uh, two different approaches using physical principles, and specifically the primary physical property of the fire, which is for process safety, is the radiant heat output, produces results that we believe to be much more accurate and lead to an understanding that far fewer detectors may be needed because in certain instances, a good amount of detection coverage is achieved. Any questions here? Okay. So next here, there we go. All right. Another advantage that I see with the use of Effigy as a modeling tool is that at Kenexis, we are not only the developers of the tool, but we are their first practitioners. As a matter of fact, I think that our company has been a pioneer in fire and gas mapping. It has used fire and gas mapping for well over 15 years. Ed, and as well as others, have been uh, voting members of ISA TR 84. And in fact, many of the principles that the company applied were in fact incorporated into the technical report, We have a number of studies that we have conducted over the years, over a wide variety of industries, several different processes, and it has been that experience that has informed decisions on the development of Effigy. So it's not a tool that is developed in isolation. The company's employees are first and foremost engineers, and I think that that shows on the final tool. Another advantage I believe you will see is that the field devices that it models are not only your conventional flame and gas detectors, but also some newer type of devices such as infrared gas imagers, ultrasonic gas leak detectors, as well as open path toxic gas detectors such as the ones made from tunable diode lasers. Another innovation that I think does help on the adoption of fire and gas mapping is that the tool is cloud-based, meaning that it uses servers that are outside of a desktop. The very first tools that were developed in the early 2000s were desktop. They were desktop computer models. And they have several limitations, especially for some of the most complex fire and gas mapping projects. It's certainly very, very difficult to do it on a desktop, even in computer rooms that are on premise at the time. And some of these computations can take days to do. You will see right now, if you have had the chance of using Effigy before, most of the computation can be done in a matter of minutes, certainly not days upon days in a row. And that does make a difference when you're working on a project, and especially when you have to work on a deadline where fire and gas mapping is just one of several tasks that need to be done. Effigy leverages the Microsoft Azure high-performance computing framework, and it just makes resources available. I don't think that we have ever been constrained by using high-performance computing from Microsoft. So all of this is fantastic. You can see that these are certainly some reasons for removing such barriers as the ones that I mentioned earlier. But the proof is in the pudding. What can we do in a real life scenario? And I wanted to show you one, and that is on a fire and gas mapping project that we had on an offshore oil platform. As you might imagine, the platform is producing crude oil, and crude oil comes from the ground as a mixture, and it's not only crude oil itself. It's a two-phase fluid. It has water, it has natural gas. It probably has a number of other impurities. And the area where you see a number of the wellheads and manifolds is replete with piping. It just looks like a mesh as shown in the photo. And in this particular case, we learned that the equipment grades are B and C. So this is an area that is at serious risk of having a fire and a detonation if a gas release were to occur and that gas release were to find a competent ignition source. So in order to model this space, we use both the conventional approach and the one with the Plume model. And what you can see here is a significant difference in the number of field devices that one would recommend with both. Let me begin here by Let me recommend here by showing the detection coverage that would be that is modeled as a result of plume modeling. As what you can see here is most of the area happens to be in green. In fact, the area modeled is just the one that I have encircled with the dash blue uh, line. And as a result of the computer model, we were able to achieve the desired detection coverage using two flame detectors. If we were to use the conventional or ray casting approach, you would notice that these pipes, because of the obscuration of the pipes themselves, are going to produce a variety of pockets where no detection by any detector would be achieved. In order to reduce risk, you would need more detectors, in fact, somewhere between 4 and 6. In many instances, these detectors may need to be placed far above the area of regard. They may require scaffolding. They certainly would need to have considerations for access, for maintenance during their life cycle. So I would say you're looking at a 2 to 3x increase in the number of detectors as a result of using the conventional approach over plume modeling. So with that, just wanted to recap some of the important points. I would say fire and gas mapping software has been a tremendous advancement for process safety. It certainly has increased the certainty around the layout of flame and gas detectors. And it is head and shoulders above heuristic and even prescriptive approaches. That being said, adoption is still a sticking point. There are a number of challenges. There's complexity, there's cost. And I think in many instances, it's just the idea that computation can be done without regard to other steps that are needed for good mapping. I would posit that Kenexis Effigy software addresses many of these challenges head on. It follows a premier norm, the Technical Report 8407. It uses the very same framework. The framework itself helps give guardrails or guidelines to the end user. So you're not using the software indiscriminately. The software itself guides you through the process. I would say it also fosters collaborations across multiple disciplines. I pointed out how detection coverage is improved as a result of the Plume modeling approach that we use. And as a result, far fewer detectors are needed in the instance of installations that have long, thin obstructions. And lastly, it uses hosted servers that make it easy for projects to be done in far shorter lead times than either on desktop models or even on-premise servers. The case, I think, is well illustrated with the offshore manifolds, where we have achieved detection coverage with only 2 flame detectors in an area where 4 to 6 flame detectors would be needed otherwise. I cannot underscore this point because especially when it comes to an offshore installation, there is a significant cost associated with every additional flame detector or any device that is added. It's not only added weight, it is added maintenance, and it is far beyond the cost of the actual device itself. Any questions?
We've had some questions in the chat here, Edward, that Ed's been addressing. So I'll just mention that there are some questions around some of the settings in Effigy to adjust sensitivity regarding modeling of flames as radiant heat emitting bodies. The response is yes. It's an input for radiant heat output is a requirement for the fire modeling. You can adjust that as well to analyze a specific scenario where you want the fire detector to be more sensitive.
That
Um,
that is absolutely true. So Effigy has a database of detection, coverage, and specifications for a number of commercial flame and gas detector models. And for flame detectors, many of the commercial models have sensitivity settings. That's not unusual. They typically have 3 to 4 sensitivity settings, and those could be adjusted. Of course, those are going to change detection coverage.
right. So, okay. So then Plume modeling can be enabled or disabled, so you can do it either way within Effigy. You would select either the point source option or the Plume option. So Effigy is capable of both. And then there was a question around licensing. Since we're the developers and users, are we licensing this to third parties? The answer is yes. Um, we do that, and that information is on our website. There's different options for licensing, so you want to check out our website at kenexis.com on that piece. So flame detector models from different manufacturers are integrated into the software.
Yes, that is correct. That is correct. That is correct. And I would say we have been quite um, accommodating. We have had manufacturers approach us and say, could you please add your our models to your software? And for reputable companies with detection coverages that have been um, validated through certification, we can add those. And by the way, if you were to develop a model, and I'm speaking as the user of the software, you can configure it to use commercial models or even a generic model. Okay, you're not limited to only one. There's actually quite a few choices.
If you guys don't mind, if I could jump in real quick and show a few of the things that the questions have been asked about. So here is a view of Effigy. So I'm just looking at a separations module here in the 3D view, and you could see that I've got a few fire detectors laid out on the screen here. Now, you could see the detectors, the mechanism to lay them out. There's a million different ways to lay out detectors. Probably the easiest one is just kind of look at a top-down view and then right-click and add a new fire detector. It'll put the fire detector in that location. But if you want to attach on the pieces of equipment using some of the more sophisticated 3D tools to be able to add pieces of equipment onto surfaces and so on, are a better way to do that. But with regards to the specific questions, you see that there are some detectors around. So over here on the left-hand side, you're going to see a list of the detectors. So the first one is fire detector 1. And I could click on it to open up the details. But before I get into that, you'll also see this eye icon where when you click on that, it's actually going to put you inside the detector. So you could see what the detector is looking at. And as I kind of scroll back, you see the back of the detector and kind of, where everything is at in relation to the full 3D model. And you can kind of go back and look around. So you see that this is a really highly densely packed area, but there's still a lot of spaces where you can see detection. Now, for the detector itself, when you click into the form, there's all kinds of things that you're going to define. So first off, when I just did a right click on the plan view, all it knows is the X and Y coordinates. When you do the more sophisticated 3D approaches to attaching the equipment, that's going to give you the Z direction also. There's a declination angle, which is the angle from horizontal. So minus 30 means we're pointed 30 degrees down from horizontal. Rotation is about the XY axis. And here is the answer to that first question that was in the chat, which is, can you define how big, essentially how big of a fire? So 50 kilowatts is a number that's used in a lot of corporate standards. And that comes from the FM 3260 test, which arbitrarily is a 1 foot by 1 foot pan of heptane. Now, 50 kilowatts is an approximation. It's actually closer to about 43 kilowatts that size of fire is kicking out. So if you want to detect a smaller fire, like you want to detect like maybe a fire that would fit in this cup, that's going to be maybe about a 10 kilowatt fire. Whereas if you're maybe in a big warehouse application, you don't care about the fire until it gets really big. Maybe you're going to want to use 300 or 400 kilowatts. And that radiant heat output setting is going to change the dimensions of the cone of vision using thermal heat transfer calculations, radiative heat transfer calculations, where our competitors who are just using ray tracing, all they're doing is geometry. They have no knowledge of the actual fire science and how different size fires generate different amounts of radiant heat flux and how that affects the detectors. So that's where you put the radiant heat output value. 50 is very common, but you can adjust that to be whatever you need for your project. And then you'll see here, we have a wide variety of manufacturers. So we could select, you know, a detector from Honeywell or General Monitors, or, you know, we've got a wide variety of different vendors here, and we're adding new vendors all the time. If there's a vendor that you use that's not on the list, let us know. We'll coordinate with them and get them into the database. Now, for each type of detector, well, you might need to select a model, whether this particular model of detector can either be multispectrum IR or a UV IR. And then you're going to want to determine what type of hazard. So for our generic manufacturer, we just have a generic hydrocarbon fire. But most of your equipment vendors are going to give you different cones of visions for different fuel types. So there's a methane plume, there's methanol, there's heptane, there's gasoline, there's oil. There's going to be usually a wide variety of different targets that you can select. And then you can select your different sensitivity settings. So I'm on high sensitivity here. But in reality, people overuse the high sensitivity setting because high sensitivity setting is going to give you a bigger distance that you're looking at, maybe a little bit of additional width, where most of the time, especially in a highly obstructed area, your limitation is not the distance, but it's the obstructions. So cutting back on that sensitivity to reduce spurious trips might be something you want to consider. And hey, if you're using Effigy, you can run your models to do all that stuff. Now, the last question had to do with settings. So right up here is the action ribbon or the navigation ribbon along the top. You can click on the study settings button, and it's going to give you default settings for fire detectors, default setting for gas detectors, but then also the general settings of how the software works. So you could do all kinds of customization, like showing tag numbers on the drawings, tool tips, determining the different types of styles of icons that you want to use for your detectors. And then ultimately what we were talking about here was point source versus plume. So point source is something that is going to be more akin to a a ray tracing, a point-by-point ray tracing that doesn't consider fire size, which is kind of the state of the art for our competitors, is the absolute worst level of performance for our software. You can make things much, much better. So instead of using point source, you can use Plume. And when you shift to Plume, you're going to need to define what the plume size is. So typically, if you're using 50 kilowatts, that's going to be representative of the 1 foot by 1 foot pan fire, which at its base is going to be 1 foot by definition, so about 0.3 meters. And the height is going to be about 3 feet or about 1 meter is what you would typically use if your target fire is a 1 foot by 1 foot pan. So then you hit Plume, you do that, you hit the update button, and now we're in the plume detection mode. So I believe I answered all the questions about how you modify the settings for different fire sizes and the use of plume. Did that sufficiently answer the questions? Or did I not get to the answer?
I think you have answered that. We did have another one come in. When you set the result type in the 3D model view to fire geographic coverage, could you limit the coverage results shown to be only limited to your desired grading area instead of showing the whole area?
Okay. So since I hope you don't mind me stepping on your presentation, Edward, but I had the software up on my computer.
Yeah, no. Go
and,
ahead. I
and,
think
and
it's a
people like to
very
see
good
the software
illustration.
in action. So
Yeah.
so when I go to result type, I can show fire geographic coverage is the way we commonly do things. And again, now we're going to be displaying our results for the plane that we selected, which is the I'll go back in a second and show you where that elevation. Now, even though the elevation is, we're showing results on one elevation to like make it feasible for you to work with. We can show you those results fully in 3D. So if I show the fire detector cone of vision fully in 3D, there it is. I don't know what you're gonna do with all of that information. So that's why we tend to put things down on the two-dimensional level. But so if I could see that on 2 dimensions, this is a little bit easier to look at it. Now, what the question was is, what does that mean for the graded areas? And honestly, I don't even know if I defined any graded areas here. Now I'm going to go to this facility, which I know has graded areas and it also has fire coverage. So there's my area grading. And now if I look at my fire geographic coverage, it's for the whole plant, but the graded areas are actually very small. Now, if I only want to see what the coverage is in the graded area, what I'm going to have to do is I'm going to have to go to a different view where I look at the fire geographic coverage in its own special 2D. We're only looking at the results in 2D at this point in time. And what I can do in this view is I could show one grade at a time. So here we only have grade B coverage. So I could look at the grade B coverage in isolation. So this is only available on this view in the 2D format. When you're looking at it in 3D, you're always going to see the entire coverage results for everything.
Ed, I think that what you have done as an exercise also underscores that original challenge that I had listed, which is that oftentimes people have difficulty in visualizing and interpreting complex outputs. And
Yep.
you have shown how by using just 2 dimensions, you're making something that could be very complicated by showing just
Yep.
the 3D detection coverage. That is actually harder, I would say, like you said, I don't know what you would do with it. And I would not show that to, say, for example, my manager after I do a project and say, look, because of this, I'm going to put 1 or 2 detectors. It's much easier to present the information on 2 dimensions.
Absolutely.
Okay, looks like we have another question out there.
Yes, please go ahead.
Yeah. So I just want to ask about the Effigy have that feature. For example, if I have a piece of equipment and I want to achieve like 90% coverage for that specific piece of equipment, and like the effigy itself, it will place the flame detector like automatically, so no need to do it manually. So it will give me the best place to play, best location to place these flame detector to achieve a higher coverage target. So it's like optimization or scenario based. So, or shall I have to do that manually to place the flame detector in each location?
Okay, well, optimization is possible. So if you wanted to do a quantitative optimization, we've done some work with Sandia National Laboratories to incorporate their Chama engine for a full linear regression optimization of the positions of the detectors, which is better than some of our competitors are using a genetic learning algorithm, which is prone to false positives. So a genetic algorithm it's very rare that it will actually get you the optimum. It will usually get stuck in a local minimum. And only linear regression is truly going to allow you to get to an optimal. But the problem is, every time that we've run an analysis using the mathematical optimum, you present that to a technician who has to install or maintain or repair this device. They will laugh at you because it will be such a bad design. Ultimately, the optimization of coverage is a small factor in comparison to other things that are more important, which is, how am I going to get power to the detector? How am I going to mount the detector? Once the detector is in place, how am I going to maintain the detector? So how can I reach the detector with a ladder and so on to be able to perform maintenance? And then where the detector is located, is it obstructing other equipment? Is it in the way of normal operations to be able to move around and access the rest of the facility? So all of those other soft factors will result in the realistic outcome that the mathematical optimum is usually an absolutely horrible place to put it from a installation, maintenance, and just usability perspective. So even though we have the algorithms to do it, we don't make them publicly available because they generally result in very bad designs.
Yeah, yeah, that is a fantastic point, Ed. I think that lack of understanding of the practical aspects of detector sighting it's just one of those obstacles, and it at some point, I think, like any other tool, you have to use fire and gas mapping as an input. Uh, and this is where you, as a process safety professional, need to apply some discretion and figure out what is optimal based on maintenance and calibration of that field device.
Thanks again, everyone, and hopefully we'll see you soon.